Well, thank you everyone for coming, and thank you, Tom, for the invitation. Tom and I met many years ago at this conference that he's alluding to. And one of the great things about conferences is you get to hang out with your colleagues and you don't actually pay attention to where you're all from. And so it took a while for Tom to figure out I was someone who he doesn't think normally talks to him. But we've been good friends ever since, and it's always my great pleasure to come out and talk. Before the talk here, I had the opportunity to spend some time eating dinner with folks who were here for the APT meeting, and that's great. It's always great to get to hang out with our friends who are in the classrooms doing the things that you're doing. I spent a lot of time meeting with the students here and talking about, what life is like when you're learning physics for the first time. And so what I'm going to tell you about tonight is the very frontiers of physics right now, the very frontiers of astrophysics. It is stuff that melts your brain. It's stuff that is hard to understand, and by hard to understand, I mean when Einstein thought of this, it took 50 years before physicists understood what he meant by it. Okay, so I'm going to tell you stuff tonight that is hard to understand, that Einstein himself didn't understand. I'm going to tell you stuff that physicists debated and argued about for 50 years, and stuff that it took them an additional 50 years to figure out how to measure after they decided they knew what they were talking about, okay? So the story tonight is an exquisite one. It's one about perseverance. It's about understanding the mysteries of nature in very fundamental ways and realizing things that you thought might be impossible actually are possible. Okay, so we're going to talk about gravitational wave astronomy for those of you who don't know the topic and just came anyways. The title here, Songs from the Stellar Graveyard, is about the sources, the things we want to learn about when we study gravitational waves, and that'll be part of the story tonight. As we go along, if you have a burning question, please ask it. I will go ahead and answer a few as we go along. I'll try and kind of constrain the conversation. But if you're confused at some moment in the middle of the talk, please ask, because if you're confused, the person next to you and the person on the other side of the room is probably confused too. And if you're confused then, you'll stay confused the whole talk if we don't try and straighten it out, okay? What will happen is 2 weeks from now, at about 2 in the morning, you will wake up and be like, oh, I wished I had asked Larson this, okay? And when that happens, my email address is right there, okay? It's there for a reason, s.larson@northwestern.edu. Send me an email. Do not wake up your spouse. They do not want to talk to you about astrophysics at 2 in the morning, okay? But you send me an email and I'll help you find some information to figure out what the answer to your question is, okay? I have a public blog there, writescience.wordpress.com. That is a blog where I talk about physics, I talk about astronomy. There's a lot of stuff about gravitational waves there. It's a blog I write for my mom, so she knows what I do. Okay, so that means if you're not a physicist, you can understand it, okay? And if you're on social media, you can certainly tweet at me at Twitter. You can go visit my YouTube channel as well. Okay, so here's what we're going to do. This is a very famous picture, very famous artist. This is a picture by a very famous artist named Mark Garlick. He's a physics professor at Warwick in the UK. And so all of us love his stuff because he's a physicist, but then he goes and does art, so it's in principle accurate. But this is his rendition of this gravitational wave event that I'm going to tell you about tonight. So we'll come back to that when we talk about the LIGO detections. So here's the storyline tonight. I'm going to start by reminding you some things about astronomy. And some of you look like you maybe haven't been in the classroom in a few years, so it's probably been a long time since you've taken astronomy. So I'm going to remind you just a couple of ways about the way we think about astronomy. I'll tell you a little bit about the great machines we've built in order to do the science that I'm telling you about tonight. And then I will tell you at the end about the things we're discovering and the things we hope to discover still with this new kind of observational science that we call gravitational wave astronomy, okay? So anytime you open up a book, anytime you open up a newspaper or see a story on the news about the universe and about the things we're discovering in the cosmos, you see pictures not unlike these that I'm showing you up here. And one of the most remarkable things about a suite of pictures like this is that when I show this slide, almost to a T, everyone in the audience knows something about what's on this slide. What's that? The moon. Is there anyone here who didn't know that was the moon? Okay, okay. How many of you have seen the moon? Okay, good. How many of you have seen the moon through a telescope? Oh, good. How many of you have not seen the moon through a telescope? Maybe that's an easier question. Okay, so there's a few of you. Okay. What's this? What's that? How many of you have seen Jupiter? Oh, fewer of you. How many of you have seen the Great Red Spot? Okay? Do you see what's going on here? All of you knew that was the Great Red Spot, but only a fraction of you have actually seen it. Okay? What's this below Jupiter? How many of you have seen Saturn? Yeah, right? Okay. What is this right here on Saturn? Oh, aurora. How many of you have seen the aurora on Saturn? Oh, right. But all of you knew it was the aurora, right? Okay. What's this? The Milky Way, our own galaxy. What's this? The Andromeda Galaxy. Okay. Ooh, okay. Any amateur astronomers in here? The Bubble Nebula, it is. Amateur astronomers, wherever you were. Okay, what's this? The Veil Nebula. Okay, and this? A globular cluster. All the students I just told about globular clusters. Okay, so on one side, there are lots of things that you are all familiar with. On the other side are things that a few of you are familiar with. But all of these are things that have not been seen by anyone unless you have access to a telescope. Now, you're looking at that right there and you're going, well, I've seen the moon. I don't need a telescope to see the moon. And you're right. You don't need a telescope to see the moon. But the surface of the moon, you absolutely cannot know without a telescope. There is not a single crater. There's not a single mountain. There's not a single canyon that you can see on the moon with your naked eye. The things that you know about the moon, and if I stopped you on the street and asked you about the surface of the moon, you would tell me, oh, there's craters, and right? You don't know that unless you have a piece of technology, a telescope. A telescope is a piece of technology that extends your bodily senses. They're bionic eyeballs. They make your eyeball do something better. They allow you to sense the universe better than your body was designed to. And by extension, all these other things that you can see in this picture, we can see, we can discover, we can learn about because we've learned to use technology to be bionic about it. And that's a big part of the story of modern astronomy. Astronomy is the discovery of what we can learn about the universe, but it's only been enabled in the last 4 centuries by the advent of technology. And the story I'm going to tell you about tonight, gravitational wave astronomy, is a story that could not be told without technology. Okay? So let's start with astronomy and technology. So this is very typical of the sorts of things that we study in astronomy. This is enabled by 2 pieces of technology. One piece is called a telescope. The other piece is called a camera. This is a region in the sky called Rho Ophiuchi. This bright yellow star in the lower right here is the star Antares. Some of you may have seen this if you look in the constellation Scorpius, which will be up this time of year late in the evening. It's the center star, the heart, the red star of the Scorpion. But this region of the sky, if you look with your naked eye, looks completely empty. But with a camera, it shows up like this. And it's awesome to look at, right? Sure, there's a lot of science here, but this is the sort of stuff you can convince your non-astronomy spouse to let you hang on the wall at home, right? It looks like art because it's colorful and it's exquisite and it has lots of detail and abstractness about it. And our job as astronomers, ever since the advent of attaching cameras to telescopes, has been to take images like this and use the information in the photograph to deduce all the things we can about what's in that region of the sky. From the colors that you see there, I can tell you the composition of the gas in the galaxy that's creating those colors. If I pick any individual star, whoops, I shouldn't put my things in my pocket. Okay, if I look at any individual star in that picture, okay, so let's look at this one right here, okay? If I just take the light from that star, I can tell you how hot the star is. I can tell you how fast it's spinning. If I know how far away it is, I can tell you how big it is. I can tell you what its chemical composition is. All from just looking at the light. And this is the fundamental issue with astronomy. No human being, as you will learn at the Apollo 11 lecture in a couple weeks, no human being has ever been farther away than the moon. But I'm telling you stories and I'm showing you pictures of things that are so far away, no human alive today or in the foreseeable future will ever visit those places. But I can tell you things with confidence about them because I can gather the light and study them. And this has been the job of astronomy for 400 years. Taking what you can see through a telescope, deducing what the universe is doing in places that are so impossibly far away, no one will ever be able to visit. That's awesome. Okay? And we're going to do a little bit better. Because even though you can see all this in telescopes, there are things in the cosmos that you cannot see in a telescope. So, this is kind of like a physics class. I know I keep asking you questions. Okay, so what is the closest star to Earth? Whoa, good job. Okay, the sun. Okay, why is the sun bright? Because it's really freaking close to the Earth. Is the sun really bright? No. If I took the sun and I put it on the other side of the Milky Way galaxy, there is not a single telescope on planet Earth that could see it. Yet. We'll talk when the 30-meter telescopes get built, okay? The sun is not a bright star. The only reason you know the sun's there is because it's close. And so if you're an astronomer and you want to study dim stars, it's a problem if your only way to study the universe is with telescopes. Because if they're far away, you aren't going to see them. That's a problem. Black hole. By definition, a black hole is an object which emits no light. So, if the way you interface with the cosmos is to point your instrument to the sky and gather light, you are hosed if you want to study black holes. Now, you're sitting out there going, okay, yeah, but Larson, every other week NASA's like, we've discovered the biggest black hole ever. Okay? And they have. But they're not looking at the black hole. They're looking at the black hole doing stuff to things you can see with the telescope. They're looking at the black hole influencing stars. They're looking at the black hole influencing gas, like the gas I showed you on the last slide. You're not looking at the black hole itself. So you're learning about the black hole indirectly, not by studying the object itself. That's like me telling you stories about my daughter. You haven't met my daughter. She's not here right now. I can tell you anything I want. And it might be true, but only by talking to her can you tell if it is true. Same thing's true here. I can study black holes by looking at them do stuff to other things. It might be true, but you're just not sure unless you can study the black hole itself. Okay? One of the most vexing mysteries in astronomy that has persisted since the 1930s is that we think 23-ish% of the universe is made up of a mysterious, attractive substance called dark matter that makes galaxies move and rotate at speeds faster than we think they should. I've just told you everything we know about dark matter. And people write big PhD theses about dark matter. But that's literally everything we know. Why? Because it doesn't emit light. All we can do to understand dark matter is look at what dark matter does to things that do emit light. It makes galaxies rotate too fast. It makes galaxy clusters move in unexpected ways. That's everything we know. So this is the problem. The universe is full of amazing and interesting and just melt your brain phenomena that we would love to understand much, much better. But our primary interface with the cosmos, our telescopes, light, is not good for these sorts of objects. But there's an out, and the out was discovered by Albert Einstein. And the out is that everything that I've told you about on the previous slides and this one, everything moves and evolves under the influence of gravity itself. And what Einstein deduced in 1916 was that if we could somehow measure gravity, we could use it as a way to observe the cosmos. And today, 100 years later, we call that observational science gravitational wave astronomy. It's different than telescopic astronomy, but the goals are the same: to learn about the faraway cosmos, sitting here flat-footed on the Earth, using whatever our imagination can build in the form of technology to help us. Okay? So let me tell you a little bit about these gravitational waves and the great machines. So you see lots of different movies and representations of gravitational waves. Most often you will see this kind of picture of the surface of a pond with ripples propagating outward. That's a fine picture. It's a good heuristic picture, but I like this one better. And the reason I like this one better is because this one shows the gravitational wave emission, and we'll talk about what it is in a minute, from two objects, in this case two black holes, orbiting around each other. And the thing I want you to take away from this picture is that the gravitational waves propagate outward. They move away from the two black holes in every direction, which is important in astronomy. It means you can use gravitational waves to study these objects no matter where you are in the universe, because they're propagating away in every direction. Now, there's two other things you have to understand. You have to understand what the content of the waves is, what it tells you about the black holes. We'll tell you a little bit about that story. And you have to be able to measure them. You have to understand what they do to the world around them so that you can measure them. Okay? And those two things are the things that took a century to understand. Okay, so let me tell you just kind of briefly what they are. I'll give you the thing that you hear us say all the time, but then I'm going to try and give you a heuristic picture, a model to carry around in your head. It's not the right picture. It's not the picture that I'll teach you when you come get your PhD with me. I'll teach you the right way to think about it. But it's the one that I think will help you understand what we're trying to do, okay? So when you first learn about gravity, when you take intro physics from me or Tom or any of the physics teachers here, we teach you that gravity depends on two things. It depends on the mass of the object, how much stuff there is making gravity, and it depends on how far away the object is from you. Okay? So, imagine my hand is a black hole. Okay? If it were this big, it would be an enormously massive black hole, but go with me on this, okay? Okay, so if my hand's a black hole, wherever you are sitting, the mass of this black hole and the distance from you means the black hole's exerting some force on your forehead in a line straight from your forehead to where the black hole is. Okay? And if that black hole got closer to you, it would pull on your forehead more strongly. And if it got farther away from you, it would pull on your forehead a little bit more weakly. Okay? Now, imagine I have two black holes. And since I have to hold my microphone, can I do it like this? Maybe not. If I have two black holes, okay, you're going to feel the force from one black hole pulling on your forehead plus the force from the other one pulling on your forehead. It'll be a little bit stronger. But the black holes are going around each other just like they do in this movie. And so one of them gets closer to you, and the force from that one goes up. And the one that goes farther away from you, the force from that one goes down. And then they keep moving, and the force goes up and down again, and up and down, and up and down, and up and down, and up and down. So on your forehead, you're feeling the force from the two black holes go up and down, and up and down, and up and down. And that is the gravitational wave, the fluctuating gravitational influence of the black holes wherever you are sitting. And what Einstein taught us is that that's happening very near the black holes, and because nothing can travel faster than the speed of light, that information propagates through the universe at the speed of light until it gets to where you're sitting, and the gravitational waves pass by you, and that gravitational influence moves. Okay, I saw a hand back here and then a hand back. So let me take those two questions, then we'll go on. Who's over here? Yes, sir. Yeah, so the question is, what I was describing, the black holes moving, are they interacting with each other? They're absolutely active. They're in orbit around each other, the way the moon is in orbit around the Earth, or the way the Earth is in orbit around the sun. So it's an orbit where the gravity of the two is keeping them bound to each other. That's a great question, but absolutely they are. But the point is just like the moon feels the gravity of the sun, you know, the Earth is close, and so it feels the Earth more, and so it moves around, right? Okay. And I saw one other hand. Yes, sir. Yeah, so the question is, are the waves we're talking about continuous? They are continuous in the sense that the black holes are constantly moving. And as we're going to talk about in a moment, if those two black holes touch and become one, they're not moving anymore, so the waves end. So you were making the analogy with water waves, that with water waves, the water does not have to move. For most water waves, the waves propagating across Lake Michigan, the water's sitting in place, just waving up and down, and the waves moving across Lake Michigan. That's very analogous to what's happening here. Okay, and we'll come back to that. Okay, let me just take one more question, and then we'll keep going. So, yes, ma'am. Yeah, so the question is what happens to the black holes when they get close together? And we'll come back to this. They get closer and closer and closer together until they touch and become one black hole. Okay, but that's part of the story, so we'll come back to that, okay? Okay, right now think of them as independent objects like the Earth and the Moon, okay? Okay, so this is the picture to carry around in your head, okay? And so the question is, what do these waves do? Okay, so I just described it to you in terms of a force. And the thing that Einstein taught us was that that's a difficult way to think about this kind of gravity. We think about gravity, as this gentleman said, as the structure and shape of the underlying fabric that the universe is made of. So what's actually changing is the structure of the universe around you. Okay, and this is what it took us 50 years to recognize, is that we have to think about gravity that way. And once you do, once you think about how things respond to the shape of the universe around them, then you can imagine how to build an experiment to measure this. And so that experiment has been realized in many places around the world, but the first instrument to do this successfully is this one that I show on the screen here. This is called LIGO, the Laser Interferometer Gravitational Wave Observatory. There are two sites that constitute the observatory. One is in Livingston, Louisiana. That's the green one that you see here. Okay, and the other is in Hanford, Washington. That's the brown one you see on the other side there. The one in Hanford is just about 2 hours north of where I grew up. So I've been to the Hanford site many times. I've actually never been to the site in Louisiana. I need to fix that sometime. So these are the machines. And what they are is they are, for the physicists, they're what we call a laser interferometer. They're easiest to think about as a Michelson interferometer. Those of you who know something about optics, they're actually Fabry-Perot interferometers. Okay, they have big resonant cavities in the arms. But what are we doing? So these instruments are huge. There's a corner building here. Okay, so this is where all the offices are. There's a visitor center. Both sites are identical. There's a visitor center here. You can go in, kind of see the guts of the machine, a little bit of history of gravitational waves and stuff. And then this building here, you can kind of see the cars for scale. This building here has a gigantic laser in it. Okay, this is our technicians with the input optics. This is our Death Star style picture here, you can see, but it gives you a sense for the size of the optics. And what we do is we take that laser and we shine it down two arms here. Okay, so this is the one at Hanford. The two arms, they're so big they stretch out of this scene there. So from the corner building all the way to the end of the arm is 4 kilometers, 2.5 miles. Okay, and in that arm is a 1 meter diameter steel tube. It was actually fabricated by the Chicago Bridge and Iron Works. The folks here in Chicago did it for us, okay? And we've sucked all of the air out of them. And we shine those lasers up and down the arms. They fly all the way down to the end of the arm, and they hit a mirror that's not unlike the one that you see there. So those mirrors are big cylinders. They're about yay big across. They weigh about 40 kilograms. Okay, and they're hanging on pendulums. They're basically suspended on thin wires. And in the current version of LIGO, there's kind of a pendulum hanging from a pendulum, hanging from a pendulum, hanging from a pendulum. There's 4 pendulums linked together. Okay, what that does is it prevents the shaking of the ground from shaking the mirror. Okay, and the reason that's important, as I'll tell you in a minute, is the measurement we're trying to make is very small. So what do we do with that laser? We shine that laser down the arm. It flies all the way down to the end of the arm, it hits the mirror and it comes back, and I time how long that takes. Okay, and I do the same thing down the other arm. Why do I do that? Because what gravitational waves do to the shape of the universe, as this gentleman alluded to, is it takes the structure of the universe and it stretches it out. Kind of like taking a piece of spandex and stretching it out. If you get a piece of spandex or rubber band and you draw 2 dots on it, the dots are your mirror, but if you pull the ends of the rubber band, the dots get farther apart, even though they're right where they started. They didn't move on the rubber band, but they got farther apart. And that's what gravitational waves do to LIGO. They stretch the space inside that arm. So the laser flying down the arm to the mirror, if the arm gets longer, it takes the laser longer to make the trip. And I can sense that. And what it does when it stretches that arm, the gravitational wave takes the other arm and it compresses it. It makes it shorter. So the laser going down that arm gets home early. And so your arms are constantly oscillating back and forth. I'm going to tuck this under my arm, right? And they're going. Okay? That's called the gravitational wave dance. It looks great at parties. Okay, I want selfies of all of you doing that. Okay, so this is what we look for in LIGO. We look for that pattern of stretching in the arms because when it happens, it tells us a gravitational wave has gone by. Now, a lot of people are like, okay, why do you need two? Because we don't believe a gravitation went by unless we see it in both of them. Why? Because the stretching I'm telling you about is extraordinarily tiny. The total length that the arm of LIGO stretches by is 1/1000th the diameter of a proton. You take a meter stick and you divide it into 1 billion bits. You take one of those bits, and without dropping it on the floor, you divide it into another 1 billion bits. And what's left is how much the arm of LIGO stretched by. Now, what did I tell you at the start of this story? Einstein thought of this 100 years ago. Einstein was a smart guy. He would have talked to Tom. Einstein was a smart guy, and he immediately calculated the number I just told you. And he said, we're never going to be able to do this. Okay? But you and I live in the future. And we got stuff that Einstein doesn't. We have lasers and computers and isolation engineers and optical systems that are capable of making that measurement. Okay? Okay, I'll tell you about the measurement in a minute, but I also work on a project to do this in space. This is LIGO built out of Lego. I also build Lego, so it's always in there. You know, I take this to Lego conventions. There's a big one here in Chicago. And people look at this and they're like, it's really not a very good model. And I'm like, and they're like, oh my gosh, it looks just like the real thing, right? So, okay. So this is called LISA. So Tom alluded to this in my introduction. I work on an international project called LISA, the Laser Interferometer Space Antenna, where we're going to build a gravitational wave observatory in space. It consists of 3 individual spacecraft, where you could think of one spacecraft as being the corner of LIGO, and the other 2 spacecraft as being the ends of those big arms. The difference is LISA is 1 million times larger than LIGO, which means we can see different stuff. It's kind of like having ordinary telescopes, but also having infrared telescopes, or also having radio telescopes. We're looking at the universe using gravitational waves, but with a different flavor of the waves, a different wavelength or frequency. And so LISA allows us to do that. We also have mirrors on LISA. Oh, this is LISA built out of Lego. We also have mirrors on LISA. This is what our mirrors look like. So we launched a test spacecraft to prove to NASA that we can do this, because they don't let you build big, expensive things unless you can prove you can do it in space. Okay, so what we did is we flew one of our mirrors. So this is one of our mirrors. It's a cube of gold and platinum. It's about 4 centimeters on its side, and it weighs about 2 kilos. Okay, and it's very, very shiny, and it floats in the middle of the spacecraft. And the spacecraft protects it from everything. The light from the sun, the heat from the outside, the solar wind, it protects it from everything. All it does is it watches what that cube does when gravity pushes it around. Okay, it's very shiny, so the lasers can reflect off of it. Okay. And so we flew this mission called LISA Pathfinder. These are 3 of my colleagues here. This is Carson Donsman, Paul McNamara, and Stefano Vitali. We flew it basically at this exact same moment LIGO made the first discovery that I'm about to tell you about. And we demonstrated that, yes, we can absolutely do this in space. So right now, we've given our ideas to a couple of aerospace companies. They're off at Walmart checking how much screws cost and stuff. And in 2 years, they'll come back with the plans. And then we're going to start building these things. Okay? So in about 10 years, LISA will be in space. And I'll come back and tell you a story about what LISA saw, the way I'm telling you a story about what LIGO saw. Okay? Now, as you might imagine, a cube of gold and platinum costs a lot. It costs like 10 million euros or something. Okay? And they don't let people like me touch that, right? They don't like me licking it and stuff. I don't know what. So my friends at NASA made me a model of this cube. Okay, and this model is made out of tungsten, because tungsten has the same density as the gold and platinum alloy that we use. So that cube in my hand there is the exact size and the exact weight as the real one that flew on LISA Pathfinder, as the real one that'll fly on LISA. And it's cool, because it's real, right? And I brought it with me. Yeah, do y'all want to hold it? Yeah, you do. Okay, so I'm going to pass the cube around, Okay? Now, I used to tell people that I just have one rule about the cube, but an 11th grader at the last talk I give made me realize I have two rules. Because I said, I have one rule, and he shouted out, "You want it back?" It's like, yes, I want it back. So I have two rules. I want it back, but the other rule is don't hurt yourself. Okay? You're welcome to take pictures of yourself with it, whatever. But if you're balancing it on your head or something, don't hurt yourself. Okay? And when you get it, you'll understand why. So I can reach you guys with my mic, so I'll start over here. It weighs 2 kilos. 2 kilos is a lot. Okay? If you're in the U.S., you don't know what a kilo is, right? But a kilo weighs a lot. So okay. Okay. So that's the technology. But the point is, it took us 50 years to build the experiment. But at the time that Einstein first thought of this, he didn't know what sorts of things could create measurable gravitational waves. Because at the time Einstein was thinking about this, the heaviest thing in astrophysics known was the sun. And the second heaviest thing in astrophysics known was Jupiter. And what Einstein really wanted to do was to build something in the laboratory that could make gravitational waves that you could measure on the other side of the laboratory. That's a very famous idea in physics. It's the way radio was originally demonstrated. That's called the Hertz experiment. Okay? And what he demonstrated is you absolutely can't do it with terrestrial-sized masses. If you and I got a 1-ton block of aluminum and balanced it on the end of a meter stick and whirled it around, we would not be able to generate gravitational waves strong enough to measure in the laboratory. You need astrophysical-sized masses to measure them. And so up until the 1970s, we really didn't know if there was anything in the universe that would make gravitational waves that we could measure. Okay? But the fact is, we want there to be. And this is really the key point here, is that anything that moves dynamically, that's changing its speed in the direction that it's moving, will generate gravitational waves. And those gravitational waves will be detectable if the masses involved are strong enough. And so this is what the game has been, trying to figure out whether or not we can measure those gravitational waves. The story I'm about to tell you has been amplified by the fact that matter, things like stars, stuff that's made of atoms like you and I, not only can generate gravitational waves, but it can also generate light at the same time. And this is very important. This has literally transformed astronomy in the last 18 months. Okay, and I'll tell you that story. Okay, so you can't quite see there. There's a name up there that says GW 170817. So this is the way we name the gravitational wave events. Astronomers always have phone numbers for the objects we're talking about. Okay, so GW means this was gravitational wave. The first 2 digits are the year, so that's 2017. The second 2 digits are the month, so that's August. And the last 2 digits are the day, so that's the 17th of August. What were all of you doing on the 17th of August in 2017? We were getting ready for the total solar eclipse. How many of you saw the total solar eclipse? Yeah, baby, that was awesome, right? Was that cool? Okay, how many of you was that your first eclipse? Okay, me too. Yeah, we were just like dumbfounded, right? So the story I'm about to tell you happened 3 days before the eclipse on the 17th. I was giving the then version of this talk that day to a bunch of amateur astronomers, literally 4 hours after I heard about what I just told you. Okay? We were keeping it a secret now because that's what we do when we make new discoveries. We keep it a secret, we check ourselves, we go write papers, then we tell the world. And so everyone thought I was just really excited because the eclipse was coming. Okay? But I knew something. I knew that the landscape of astronomy was about to change. And literally it changed. The entire astronomical community flipped out because of what I'm about to tell you. The paper we wrote about this story has 4,000 astronomers on it. 1/3 of all the professional astronomers on planet Earth participated in this paper. It literally changed the landscape of astronomy. Okay, so let me tell you what we saw. So the discovery was made by LIGO, and the important part is it was simultaneously made by a satellite NASA flies called Fermi. LIGO is a gravitational wave interferometer. We detected a gravitational wave signal, which I will see you in a moment, or show you in a moment. Fermi is a gamma ray satellite. It looks at the universe with light, but with gamma ray light. Light that is so energetic your eyeballs can't see it because the gamma rays go right through you. Okay? Lots of energetic phenomena make gamma rays. There are many mysteries in gamma ray physics that we've been trying to understand, one of which is something called a gamma ray burst. Gamma ray bursts have been known since the 1970s. They were discovered by the military, who thought they were the Russians testing bombs. But then they decided, nope, the Russians can't be testing bombs in space. They don't have that many rockets. Okay? And so after about 10 years, they said, okay, this isn't the Russians, we'll tell the astronomers. Okay? And literally, my entire career in astronomy, we have not known what gamma ray bursts are. But now we do. Okay? Because we made this simultaneous detection. So let me show you the data, and then I'll tell you what they are. So the top figure there, these are the only scientific plots I'll show you. Okay, so don't get scared and start having panic attacks. Okay, this is the LIGO data. Okay, and this is what we call a spectrogram. Now, spectrograms are something that we're very used to in LIGO. We look at these things all the time, and someone shows me that right away, I can tell you exactly what it is, because I know. But you all have seen spectrograms before too. You just don't realize it. Okay, the most common place most of us see spectrograms is on our stereos. Right? You go look at your stereo, it's all those little blinky lights that go up and down and up and down and up and down. Okay? On one side, those lights going up and down is telling you how much bass sound is in your audio. And on the other end, those little lights going up and down are telling you how much high frequency treble sound is in your audio. And in the middle, those little lights are going is how much in the so-called mid-range, where voices typically reside. Okay? So if you look at any up and down stripe on this chart, it's telling you how much bass, how much mid-range, and how much treble is there in this gravitational wave signal. And you'll see over here at early times, it's mostly in the bass, and then it kind of goes up to the mid-range, times increasing as we go along here. Here's 30 seconds, 25, 20, 15, 10, 5, and then suddenly it jumps up into the treble range. So that shape is very characteristic of things in orbit around each other, the orbits slowly getting smaller until they merge and become one object. We call that a chirp. The signal starts at low frequency when the orbit's moving really slow. As the orbit goes faster, the signal goes to higher frequencies until they reach their moment where they merge, and it's very high frequency. So if I'll show you this a little later. If I turn this into sound, it goes whoop. That's what we call a chirp. Okay? So this is what the gravitational wave data looks like. I'll show you the very first detection as well. And when you've done this as long as I have, you look at these things, you know instantly what they are. Okay? And so we look at this, and we knew right away that this was what we call a neutron star binary. Okay? And I'll tell you what that is in a moment. This is the gamma ray data. This shows in a very exquisite way why I am not a gamma ray astronomer. Because this is what they do every day. They don't look at pictures. They look at this. They're like counting gamma rays. That's all they do. Like, oh, look, we got 980. Oh, yeah, we got 750. Oh, yeah, that's 995. Okay, blah, blah. Oh, there's 1,010. Just all day long, just counting gamma rays up and down, right? Up and down, up and down. Here's the LIGO event, okay? And 1.7 seconds later, they flipped out because their gamma rays jumped from 1,000 all the way up to 1,500. Oh, my gosh. Okay, they don't get that excited. Well, they probably do. Okay, but what actually happened is that one of our former postdocs from Northwestern, a guy named Tyson Littenberg, he works on gravitational waves. He got his degree at Montana State just like I did. He now works at the Marshall Space Flight Center, also working on gamma rays. And he saw this plot, and he knew about the LIGO discovery. So he sent an email that said, hey guys, did you happen to notice that this gamma ray burst went off 1.7 seconds after the LIGO event? And we're all like, what? Okay, and literally the entire astronomical community melted down. Because this was the first time in history that we had ever seen a gravitational wave event at the same time we had seen something in telescopes. And that meant every astronomer who had access to a telescope in the world wanted to point their telescope where this was to see if they could see something. Now, this happened at about 5 o'clock in the morning here in Chicago. And that meant most of the telescopes in the world could not see the point on the sky where this happened. So for the next 10 hours, those of us in LIGO and our collaborators in Europe who work on a similar experiment called Virgo that works with us, we took all of our data and we narrowed it down to where this thing happened on the sky. And then all the telescopes in the world pointed there. Okay? Because we knew it was this thing called the neutron star binary. So let me tell you about the neutron star binary and then I'll show you the data. So what's a neutron star? A neutron star is the skeleton of a dead star. Stars are like people. They live their lives, they get up in the morning, they burn hydrogen, they go to bed. They get up in the morning, they burn hydrogen, they go to bed, right? That's their job. All they do is burn hydrogen. But when they get to the end of their lives, they're done, and they die. They die a little more exciting than most of us. They explode. Okay? And when they explode, they take everything that was in their core and they compress it down into something about the size of a city. But that thing, that skeleton that's left over, that's been compressed down to the size of the city, weighs about 1.5 times as much as our sun. So it's very dense, and its gravity is very extreme. So if I were to take the College of DuPage there and put a neutron star on top of it, this is how far it would extend. It would fit within what you can see standing out in the front and looking to your left and looking to your right. Okay? They're extraordinarily tiny, but they're extraordinarily exotic. We had our artists at Northwestern work with us. This is a representation of the neutron star as if it were hanging over the city of Chicago. So how many of you have been down to Adler, right? If this is the skyline is viewed from Adler. If the neutron star was hanging over the city of Chicago, you could see the whole thing. If you could somehow stand on the top of the Willis Tower there and reach up with a teaspoon and grab just a teaspoonful of this material, something the size of a sugar cube, the mass of that sugar cube would weigh 30 times more than every man, woman, and child on planet Earth. If you could take a walk across the surface of a neutron star, you certainly couldn't. The gravity on the surface of a neutron star is like 100 billion times stronger than the gravity on Earth. But if you were taking a walk across the surface of a neutron star, hanging out at springtime, and you had the misfortune of encountering a cliff just 1 millimeter tall, and you accidentally fell off that cliff, by the time you reached the bottom, you would be traveling 130,000 miles per hour. These are not ordinary objects you encounter in the laboratories here at school. Okay, they're exotic. And this is why, as astronomers, we're so intensely interested in them. The only way to study them, the only way to understand the physical processes that make these things tick, is through astronomy of the sort that I'm telling you about right now. We've seen these things with radio telescopes before, but we've never watched two of them merge together and tear themselves apart until now. And that's exactly what they did. They were observable in LIGO for about 100 seconds. At the moment that we first detected them, they were about 400 kilometers apart. They were going around each other about 50 times a second. Over the course of the next 100 seconds, they were emitting those gravitational waves in that chirp signal that I showed you. And we were detecting those here on Earth. And what those gravitational waves do is they make the orbit get smaller. It shrinks. And as the orbit shrinks, they go around each other faster and faster. That's what makes that gravitational wave signal chirp up into that treble and midtones that you saw in that plot. And then as they get really close together, they start to sense each other's gravity very strongly, that hundreds of billions of times Earth gravity. And it distorts them. And as they begin to distort, they eventually reach out and they touch. And at that moment they touch, they explode. And they launch that jet. That's the gamma ray burst that you see. Over the next few days, and indeed many weeks, the shattered remains of the star expand outward and emits light. That's an event that we call a kilonova. And we can still see the remains of the kilonova today. It's still fading. All of that super dense material that was in the neutron star is expanding outward. and recombining to form atoms. And one of the great discoveries that we worked on very hard at Northwestern, actually, is the fact that from the gravitational wave data, you can calibrate the light from that kilonova and tell how much chemical elements, heavy materials, were made as that kilonova expanded there at the end. Okay, and so if you read about this or you've heard about this, you hear us say we made a lot of gold and platinum in this explosion. That's how we know. Because we can take the light, which tells us there should be things like gold and platinum. We can take the gravitational wave data, which tells us how much stuff there is, and the two together tell us something that we couldn't say before. That's why this is so transformative. We can say things about the universe that were impossible before we had the gravitational wave data. Okay, yes, sir. So beforehand, we knew that stars exploded and created some of these heavy elements. What we couldn't account for was the precise balance of all the elements we see in the universe, right? That's a mystery, because if it all comes from stars, you have to see a certain number of stars exploding, and we were pretty sure we weren't seeing enough stars exploding. And so now we have these kind of competing processes. And so now the question is, okay, how many stars explode? How many neutron stars merge? How much do each of them contribute? And is the balance the right balance that we see in the universe? That's the kind of story we're trying to understand. Okay, does that make sense? Okay, everyone good? One more, yes, sir. So I'm not going to be coy, but this is the fundamental problem. It is not the ether any more than light is not the ether. So let me appeal to light. If a beam of light propagates through space from me to you, what's waving with the light? Yeah, it's the same question. It is a physical phenomena that doesn't have a material representation that you and I can represent on a lab bench. But that doesn't mean it's not real, right? There's a direction between me and you that you and I describe abstractly as front and back and left and right. But I can't put something on my bench that's front and back and left and right. That doesn't mean it's not there. Right? And this is what we absolutely struggle with when we measure things like light and when we measure things like gravitational waves, is we have to ask ourselves, do those abstract things that aren't tangible and touchable affect the world around us? And we often have ideas that suggest maybe they should. The ether is one example. And we do what every good scientist should do. We say, if this is true, it should have this kind of influence, and we go do an experiment to see if it's right or not. And we've done that with the ether, and it's not there. But this idea about gravitational waves, the idea that the universe is space and time somehow abstract and empty and nothing between me and you, and it can stretch, it can be tested in the ways that I'm telling you here, and it's apparently the right kind of idea to describe the structure of the universe. Right, and Einstein's point in that is that there are experiments you and I can do where I can fool you into thinking space is warped, and you won't be able to tell the difference. So if I put you on a rocket and you throw your keys up in the air, they fall to the bottom, okay? What is true, however, is if I put you on a rocket, there's not a way to mimic gravitational waves, right? You can't throw your keys up in the air and have them come down in a rocket and tell the difference with gravity. I can't make gravitational waves on a rocket and fool you. So that's an interesting distinction. And these are subtleties in general relativity. They're what we call, so this is technical language, we call them invariants. They're things that everyone can agree on no matter what they're doing. And this is an example of that. This is why we argued about this for 50 years, because we couldn't decide they were invariants. Yeah. Okay, good. I'm still alive, folks. Okay, so here, let me polish off the end of the story, and then I'm happy to take questions for as long as we want. After about 10 hours, the sun went down. The spot in the sky where we thought this was came up. It was actually very close to the sunset, so we only had like an hour at night to observe it. But that galaxy right there had this little arrow pointing right at the thing that was the gravitational wave event, okay? That light there is the light from that kilonova explosion. Okay, so this galaxy is called NGC 4993. Those of you who are amateur astronomers, it's right on the border of Hydra, Corvus, and Virgo. Okay, so these ellipses here are the ellipses that LIGO told the astronomers to go look in. And about 6 telescopes on that first night located it there around NGC 4993. Okay. I'm also an amateur astronomer. I'm a professional as well as an amateur. So this is my telescope. This is called Cosmos Mariner. I've apparently seen this galaxy. I went and looked at my notes, and the only thing it says about this galaxy is dim fuzzy blob. So it's apparently not a very exciting galaxy, but it had this gravitational wave event in it. So I need to go look for it again this spring as soon as I can get out with my telescope. So, okay, let me show you these events. Let me show you the data in a slightly different way, and then we'll call it an evening here. So this is what these gravitational waves look like. Okay, so the wave form, the representation for how strong does the wave look and how does it change over the time, looks like all of these wiggles. And so this is an out-of-date graph now. We now have 11 of these that I could put up here and show you, but these are the first 6 at the time we discovered 1708-17. Those top 5 are all black holes merging with other black holes. The first discovery that LIGO made, 1509-14, 2015, September the 14th, okay, was 2 black holes merging together, okay? Everyone after that we had seen, for the next 6 of them, I think, were black holes. And then we saw the 2 neutron stars, okay? Now, I told you that when we see this data, we know exactly what we're looking at, because I've been doing this for a couple of decades now, and I recognize what 2 black holes merging together look like. There's this very famous interview with Kip. So Kip's one of the guys who won the Nobel Prize, Kip Thorne. I was in his group when I was a postdoc. Someone took that top plot I showed you there and showed it to Kip. They just handed it to him, and Kip's like, oh my God, we've done it, right? Because he knew what he was looking at. He knew this was 2 black holes, okay? The problem with this is that if I send these to the editor of the Chicago Tribune, they're like, go away, kid, you bother us. Because they, like you and I, grew up learning about the cosmos through the eyes of Hubble. They want pictures, like those pictures I showed you on the very first slide. The pretty pictures of the galaxies and the nebulas, okay? And things that remind them of their days in physics classes, just don't do it for newspaper editors, okay? And for lots of you, if I hadn't have been here kind of helping you along and convincing you this is cool, they may not, right? If I had led with this, you'd be like, oh my gosh, I can't believe I came to this talk, okay? So what we struggle with is how do we help you experience this and be able to recognize this as easily as we do as gravitational wave astronomers? And I alluded to this earlier. The way we do it is we can take this data and turn it into sound. Because one of the things you learn right away, the first year you take physics, is that waves are waves are waves. Every wave, no matter what it is described mathematically in exactly the same way, by its frequency, by its amplitude, by its wavelength, by how it changes in time. And light waves and sound waves and gravitational waves all mathematically look exactly the same. And in particular, your phone has a whole bunch of wiggles on it that look just like this. And your phone knows how to take those wiggles, and when it pushes it out through the headphone jack, to turn it into the sound of Katy Perry or Led Zeppelin or Glenn Miller Band or whatever it is you listen to. So if I stole your phone and replaced your Katy Perry with these, then when you tried to play Firework, you'd hear black holes merging. So I can do that for you, okay? So I'm going to play you 2 sounds. I'm going to play you the first event, 1509-14, and then I'm going to play 1708-17, so you can hear the difference. And what the lesson I want you to learn from this is that you can hear the difference. Because you have spent your whole life learning how to take sound and tell the difference between me talking and the person sitting next to you talking. And in a very similar way, if I play you a black hole and a neutron star, you can tell the difference. Your brain's been trained to do that. If I just show you the graphs, you're like, oh, they kind of look the same, okay? But your brain knows how to tell the difference. Okay, so let me play the sounds for you, and then we'll call it an evening. So here is the very first event. These are the spectrograms. You see that chirp shape that we showed you? Here's the waveforms. These are the actual data from the 2 sites, Hanford and Livingston, just like you saw on the previous graph. And this is a movie. It will play from left to right, and you'll see it's about half a second long. So in the first half of the half a second, what you're going to hear is, we call that noise, okay? And it's literally noise. It's like static on your radio in the olden days when radios had statics on them, okay? Yeah, the people with olden day radios laugh, right? Okay, but when you get to here, the signal, the thing that we want, becomes louder than the noise, and that's when you hear that chirp, okay? Now, the chirp's going to play twice in succession. The first time it's going to play it actually like the data is. It'll sound like a heartbeat, just a thump. And then it'll repeat, and all we've done is we've pushed the sounds a couple of octaves up the piano, so it'll be a little bit higher pitched so your ear can hear it. Okay, so I'll play that, and then we'll play the neutron star. That's what gravitational wave data sounds like if I turn it into sound. And if I play every one of those black holes that I showed you on the first picture, that's on this picture, they would sound a little bit different. Because the sound you hear depends on how big the two black holes are and how far apart they are when they first start merging and when they do merge. It depends on whether or not they're spinning, right? It depends on how far away they are from Earth. All of those things affect the sound, but your ear is sensitive enough to hear the difference, okay? Now, the neutron star sounds a little bit different. So, the neutron stars are only about 1/30th as massive as the black holes. So the gravitational wave signal is a lot weaker. So right now, this is in that early phase that I was telling you about. It's playing. Actually, if you listen on the headphones, you can hear it, but in this room, you can't. Okay? But the data is much weaker, and they're much farther apart, and they're not interacting as strongly. But LIGO is still capable of making this faint measurement. Okay? But as they get closer and closer together, the gravitational waves get a little bit stronger. Can you hear it? And they get stronger, and stronger, and stronger. Until they chirp. That's a chirp. Okay? You can tell the difference between the black holes and the neutron stars. Okay? Your brain has been training itself for decades to be gravitational wave astronomers. So I actually have these things on my iPod, right? So they spin up, and my 14-year-old's like, really, Dad? And I'm like, this is the music of the cosmos, son. It's awesome. So, okay, I lied. Let me show you one more graph. This is the current state of the world. Okay, this graph, this is a tool that you can use on the web. We built it at Northwestern, and you can go play around with it and ask it to plot anything you want. But it shows every stellar mass black hole we know and all the neutron stars that we know. And so at the top there are all the black holes in purple and blue, and in the bottom are the neutron stars in yellow and the two orange ones. So the difference is the orange ones are the ones we've discovered with gravitational waves, and in the black holes, the blue ones are the ones that we've discovered with gravitational waves. Now, with the black holes, there's a great mystery in that we discovered, if you had asked me on September 13th what the heaviest black hole that we will see is, I would have told you 15 solar masses-ish. And the first two black holes, and indeed many of the ones we've seen since then, are 30 solar masses. So the great mystery in astrophysics right now, which lots of us have ideas about, we have several ideas at Northwestern that I think are probably the right ones, is how do you make these things? Because up until 2 years ago, we had never seen them, so we'd never really thought carefully about how does nature make these? Okay, and so now the big business is trying to detect enough of these that we can figure out how nature makes them. The neutron stars, you'll see they all exist down there near the bottom. And the thing I want you to notice on this plot is that there is no neutron star heavier than about 2 times the mass of the sun. There is also no black hole lighter than about 5 times the mass of the sun. And the question is, really? Okay, we call that the mass gap. And the real question that we have is, does nature forbid black holes from being lighter than 5 times the mass of the sun? And does nature forbid neutron stars from being more than twice the mass of the sun? We don't know because we've never seen something between 2 and 5 solar masses. But you'll notice those 2 neutron stars merge to form that question mark right there. And it sits right in the middle of that region we would like to know about. And so the argument we have right now, most of my colleagues think that's a black hole. Just to be contrary, I think it's a hypermassive neutron star. Okay, but the truth is we don't know. Okay, and if this is a process by which you could make black holes, the question is it the only way to make black holes that sit in the mass gap? We don't know. So these are the kinds of mysteries that keep me up at 2 in the morning. So, right? Okay, similar to the ones you're going to have at 2 in the morning. So, okay. People always ask me what's the most important thing about LIGO. And the thing I like to remind everyone is that LIGO is awesome. It melts your brain. It kind of defines the frontiers of what we know about astrophysics. But the most important thing about LIGO is that it is an accomplishment that we as humans made together. And it is not the way you learn to think about science when you were taught science. LIGO is an experiment that literally takes thousands of people to accomplish. And even though the papers have 1,000 of us authors, us physicists on it, there are literally 10,000 people behind us who made this possible. The folks at Chicago Bridge and Iron Works who built the tubes, the optical engineers, the information technology people who move our data around, the people who do our mirror coatings, right? The construction engineers who built the buildings at the facilities, right? Literally tens of thousands of people are behind every science experiment you hear about. And that's true of LIGO, it's true of the Large Hadron Collider, it's true of the Hubble Space Telescope, it's true of the Curiosity rover on Mars. Thousands and thousands of people work to make this happen. And lots of them are scientists like me and Tom and the other physicists in the room. Lots of them are ordinary folks just like all of you who are just doing their jobs, but their jobs happen to contribute to this great endeavor that we call astronomy. And it's something that I like to remind you all of. It's something that you've contributed to or your friends have contributed to and you don't know about, and we couldn't have done it without everyone standing behind us. So this accomplishment belongs to everyone, and you shouldn't forget that, okay? Okay, so I'm going to end there. I'd like to leave you with a few things to read. There are books beginning to appear about gravitational waves. For a long time, there have not been many. This book here on the all of the one on the left and the one on the right have both won Science Writing Awards. Marcia Bartusiak is a very great science author at MIT. This book by hers, Einstein's Unfinished Symphony, is about building LIGO and how hard it was. Okay, she published the first edition of that book before we made the first discovery, but there's now a new edition that has a chapter about the discovery on it. So if you go to the library to get this, or if you order it, make sure you get the second edition so you can hear the story about the discovery. The book on the right is not just about gravitational waves. It's about the sort of stuff you and I were talking about space-time and the stretching of the universe and all of that. It talks about black holes. It talks about wormholes, all of that sort of stuff. It was written by Kip. And it's been very popular for many years. It's probably the best public level book about relativity that you can get. This book in the middle is one of the new books about gravitational waves that I like. It's by Brian Clegg, who's an award-winning science author from the UK. I do like this book quite a bit, and there are others appearing, so there are many I could have put here, but this is a particularly nice one. If you want to help us, not you science people, well, you science people can help us too, but you, the rest of you, if you go to gravityspy.org, this is a citizen science project that is helping us understand how LIGO behaves so we can teach the computers on LIGO to recognize gravitational wave signals. This is a spectrogram, okay? I've shown you several of those. And that spectrogram signal there is not a gravitational wave signal, but the computer thinks it is. Okay, and so what our citizen science project is we show you lots of spectrograms, and you say, this one's what we call a blip, and this one's what we call a koi fish, and this one's what we call a whistler, and this one's what we call paired doves. And we take them all to the computer, and we say, see, not these. Okay, so you're teaching the computers to be better. Okay, and what our project is, we do this in collaboration with the folks at Adler. Our project is to teach the computer to ask you for help when it doesn't know what it's looking at. Okay, so it's this kind of feedback loop between people and computers. But citizen science projects are all about image recognition like this. because you are very good at recognizing images and computers are not. Okay, and so we use you to teach the computers, and it makes our life very easy. We've discovered many things in LIGO as a consequence of this. We have about 15,000 people who have done this with us. They range in age from about 5 to 105, and they've done 1.5 million classifications. Okay, you can do it on your phone while you're riding the train, right? When you're up at 2 in the morning, your spouse will want to talk about astrophysics, do Zooniverse with us. So, okay. Here's a set of websites over here. There's my blog at the top. You'll see links there to the LIGO YouTube page. That LIGO detection page there will take you to many of the images and the sounds that I just showed you. Okay, and then the LISA site there at the bottom, that'll take you to both the US and you can get to the European LISA site if you want to learn about LISA. And then, what was I going to tell you about this? One other thing I was going to tell you there. I can't remember. Anyways, go to those. Oh, sorry. At my blog, if you go to my gravitational wave posts, at the bottom of each of my posts, I've linked out to other blog posts by my other colleagues in LIGO. And so you can go read what all of them had to say about it if you don't believe me. So, okay? Okay. I am going to end there and say thank you, and I'm happy to take questions as long as you let me. So. Okay, so the question is, I showed you about 5 chirps, and then why aren't there any? So we've published our full catalog now. There's about 11, okay? But all of those events come from what we call observing runs. So right now, when we turned LIGO on, we run for a short period of time, and we keep track of all the issues we have. Oh, when this air conditioner turns on, it makes a weird signal. Oh, there's a vacuum leak over here. Oh, this mirror shakes too much. We keep a whole list of this. And at the end of the observing run, we shut it off, we go in, we fix all those problems, and then we turn it on again. Okay? So those events ended in 2016 at the end of what we call observing run 2. And observing run 3 started on Monday. So we are running again right now, and there will be new events in the near future. Okay? And at the rate at which they occur is yet to be determined, but there will be new events. So the question is about the overlap between CS, computer science, and astronomy, and whether or not that is a fruitful future career direction. Okay, so I'm going to say the answer is yes, because physicists don't know squat. We know a little bit, but we really need people who are trained in computer science. And that is because not only with experiments like LIGO and LISA, but the future of astronomy is about what we call big data. We are collecting data at a prodigious rate, and we can't analyze it fast enough. Okay, so let me tell you about an upcoming experiment. So right now in Chile, they are building a telescope called the Large Synoptic Survey Telescope, LSST. LSST's camera is 9 square degrees. Okay, so that's 18 moons by 18 moons. It's about this big on the sky. And it will take a picture of every point in the sky in 5 different colors once every 3 days. It will generate, I don't remember the number, it's like a terabyte of data a night. There are going to be 10 million transients every night, 10 million events, something getting brighter unexpectedly in the LSST data every night. Humans can't handle that. Okay? We need computer algorithms to be able to sift through the data, decide what's interesting, decide what's not, decide when to tell the humans. The question is, can someone in the Midwest stay in the Midwest and do this? The answer is yes, because universities all over the world do this. So we have LIGO groups at Milwaukee, we have LIGO groups at Northwestern, we have LIGO groups at University of Chicago, we have LIGO groups at UIUC. We have an LSST group at Northwestern. There's the National Center for Supercomputing Applications at UIUC. So this is, there's a LIGO group and a Zooniverse group at the University of Minnesota. They are all over the place. So your key bet is universities. You can also go to the federal labs. We have a dark energy survey camera group at Fermilab. Right? So there are opportunities. The key is to get connected to them. And the key there is to just find scientists who know the right people to talk to, and you know me now. So you just email me and say, I saw you at COD, you said you could help me. And I'll be like, yeah, let's find you a group to talk to. So the question is, how long did it take the gravitational waves from the neutron star event to get to Earth? Is that what you're asking? Yeah, so this was 40 megaparsecs away. So 40, that's 40 million, so that's about 120 million light years. So it took 120 million years. So those two neutron stars collided, I think they were still dinosaurs, yeah. Okay, but the dinosaurs got their act put together and built LIGO before they got here. Okay, so the question is, how can we tell the difference between neutron stars and black holes? So there's two things. One is the length of the signal. So the black hole signals you noticed were all just kind of 2 seconds long. Okay, the neutron star signals, in the LIGO, full LIGO signal was 100 seconds long. And that's a statement about their size and how they interact with each other. So since they're lightweight, they are able to go around each other longer before they touch. That's the primary way that we can tell the difference. The other way we can tell the difference is the size of the wave depends on the mass of the wave, the mass of the stars. And so we could tell right away that they were neutron star masses, not black hole masses. At the moment that, yes, that's right. We know, we have predicted ahead of time what the signals will look like. So the question is, how do we suspend the Lisa cube on space? So if you looked at the cube, you saw there's little divots on the ends of it, okay? And if you held the cube, you're like, wow, if you put that on a rocket and you fly the rocket and it flies around, it'll do a Wile E. Coyote job on the rocket, okay? So what do is we clamp it down, okay? And we hold it clamped down until we get into orbit. And then there's these little fingers that go in those little holes. They extend out till the cube's where it's supposed to be, and then they retract and leave the cube floating. No. In fact, you want the magnetic fields are a problem. The reason it's gold and platinum is because it has this property of how well it couples with magnetic fields is very weak for gold and platinum, this particular alloy, and that's why we use the gold and platinum. So the question is, what's the limit to how far away we can see black holes? That depends on the mass of the black holes, okay? When we reach design sensitivity, I actually don't know what the maximum distance is. It's pretty far. These black holes that we saw, the first ones, the 30 solar mass ones, were 1.3 billion light years away. And again, if you had asked me on September 13th how far away we'd be able to detect them, I would have told you not that far. But these were heavier than expected, so we can see them farther away. Okay. There will be a time in the future, I think not until we upgrade to A+, where we will be able to see black holes like that all the way to a redshift of 10 or something. So it's really, really far away. LISA will be able to see black holes all the way to the edge of the visible universe. So the question is, what's different about LISA's performance compared to LIGO? So there certainly are advantages to being in space. As you alluded to, we don't have ground shaking to worry about. But LISA fundamentally is observing black holes that are different than the LIGO ones. So in particular, these black holes, when LIGO sees these, they're very close together, and they're going around each other about 10 times a second. LISA can see these same black holes, but at a much earlier time in their lives, where it's taking them about 1,000 seconds to go around each other. So their orbits are much wider. Okay, so detecting them at that stage is very different than detecting them at this stage. But the ones that we can see to the edge of the visible universe, those black holes are the kinds of black holes we see at the centers of galaxies, and they weigh 1,000,000 times the mass of the sun. So the signals are enormously strong compared to the signals from these. That's why we can see them so far away. Yeah, so the question is, are we going to build more LIGOs and in the southern hemisphere? Yeah, so right now there is a detector in Italy outside of Pisa called Virgo. There is a detector the Japanese are building in Japan at the Kamioka mine. That's called Kagra. It will be on in a year or so. They're almost done. They're testing right now. We are building one in India, an identical one to LIGO. We have a LIGO in the box, the optics and the lasers. The Indians are building a site, and we're going to take the LIGO in the box and put it in at the site. So that'll be LIGO India. That's as close to the southern hemisphere as we're going to get. There has long been plans to build one in Australia, but the Australians are trying to figure out what they're going to do right now. But that one's called IGO, A-I-G-O, the Australian Interferometric Gravitational Wave Observatory, and it would be very beneficial if it were to happen. Yeah. So, okay. Okay. I'm happy. I'll stick around for those of you who I didn't get to. So.